All right, in the final part of this lecture, we're going to cover chi-square analysis. And so the idea behind chi-square analysis is it provides us with a statistical test to determine whether or not a ratio is followed. So we do not get perfect data. We do not have an infinite number of p-plants. So for example, when we do the F2s and we study the F2s, we do not actually have an infinite number of F2 plants that we look at. And so I'm just re-showing this table of data from Mendel, but you'll notice that, when he did the study of the inheritance of these 7 different characters, he had a large number of plants that he looked at, so on the order of 8,000 plants for some of these traits, but these do not result because of stochasticness in the inheritance. These do not result in perfect 3-to-1 ratios. So in this last column we see, for these first two, it's 2.96 and 0.01. So this differs by 0.04 from the 3-to-1, and this differs by 0.01. And then in these other ones, we have even a larger deviation. So I guess that's negative 0.04. So, this one right here is 0.15. And this one right here is negative 0.16. And so, some way as experimenters, we don't want to just say, this is good enough, it's close enough to 3-to-1, but we want to have some sort of way to say, with some sort of statistical certainty that, that this ratio that we observe is consistent with a 3-to-1 ratio. And so one thing you might notice from this data is that in the situation where there was a large number of F2s, so when there was 8,000 F2s, the deviation was much smaller than the case when there was only approximately 1,000. So in this case, it was almost, on average, it was almost 10 times larger was the deviation. And so this is kind of a known property of statistics, is the more that you test, the more individuals that you test, the closer to that ratio that you expect to get. The less individuals that you test, the further away from the ratio that you expect to get just by chance. So how do we do that? So this is where the chi-square test comes from. So is the data that we observe actually following that ratio? And so the chi-square test allows us to do that. And what it assumes is that the initial assumption is called the null hypothesis. So at some point, you all will have to take a statistics class that gets into this in much more detail. But the idea is that our null hypothesis is that the data fits the 3-to-1 ratio. So we assume that the data we see fits the 3-to-1 ratio. And now we calculate a probability that that 3-to-1 ratio has in producing the values of data that we see. And so if we reject that, if the chi-square test rejects that, then basically what it says is that the data that we see is so far away from that 3-to-1 ratio, or whatever ratio we're expecting. So if we were doing a dihybrid cross, we'd expect 9-to-3 to 3-to-1. Then we would reject the null hypothesis, and we would conclude that the data doesn't actually match that ratio. So some of the important things that you need to know is the sample size. You need to know the expected ratio. You need to know the data, so the actual data that you observe. And then you need to know what's called the degrees of freedom, which is typically just listed as df. So here's an example of a monohybrid cross and a dihybrid cross. And so in the first case, we have our sample size is 1,000. And in the second case, our sample size is 1,008. Our expected ratio is listed here. So we expect to have a 3-to-1 ratio. So we expect 3/4 of the progeny to have the dominant phenotype, and we expect 1/4 to have the recessive phenotype. For the dihybrid, it's 9-to-3 to 3-to-1, so we expect 9/16, 3/16, 3/16, and 1/16 to have the 4 different phenotypic categories. So now we have the data, and so the data we list here. So how many did we have the dominant phenotype? So 740, and then 260 had the recessive phenotype. So this again adds up to 1,000. What is our expected value? So our expected value is just 3/4 times our total. So 3/4 times 1,000 is equal to 750. And then how many do we expect to have the recessive? Was 250. So now we've listed the actual data in this column, and we listed the expected data in this column. Then we calculate the difference. So we just subtract these two numbers, so -10 and +10. We square those numbers to get 100, and then we divide those numbers, this number right here, by this expected column right here, and then this gives us this number, so d squared divided by e. And then so you'll notice in this first row we divided by 750, and the second row we divided by 250. We add these up together, and in the end we get this chi-square valued of 0.53. So by doing this, we end up with this chi-squared value. Again, we can do this for the dihybrid cross. So these are the observed data, add up to 1,008. Our expected is 9/16 times 1,008. So this times this number times this number, and that is equal to 567. This times this equals 189. And so these are our expected categories. Again, we subtract them from each other, this minus this, and then we square it to get 464, 441, 49. And then we divide this, would be by 567. This would be by 63, etc. And then this gives us our statistic, which by summing up, we get our total chi-squared statistics. So how do we go from here to here, chi-squared to probability? And so you have to know the final thing, which is the degrees of freedom. And so it's equal to the number of categories minus 1. So there are 2 categories here. So the degrees of freedom is 1, because there's 2 categories. And then for the dihybrid cross, it's 4 possible categories minus 1, so it's 3. And so now you just have to use these tables, and you have to use these tables to determine whether or not we should reject the probability. So this is a table of the value, and then this is kind of a graphical depiction of it. So you can either, for example, follow this line. So this is the line for the degrees of freedom. So we calculated 0.48. And so if we go to right here, sorry, the chi-squared value is 0.53. And so if we go up to here, the p-value, because we went up to the degree of freedom of 1, the p-value is approximately 0.48. And then here it was 4.16. So 4.16 is approximately right here. And then we go until we reach this line right here. And we choose this line because this is the degree of freedom equal to 3. And then if we trace back this way, we get a number somewhere around 0.2 to 0.3. And so 0.26 was the value there. So that's one of the ways you can do it. Or you can use one of these tables and then determine, is the chi-square value less than or greater than the probability of 0.05. And so this again was 0.53. And so this would fall within this range right here. And then this was 4.16. And so this, again, would fall within this range right here. So only if the chi-square value is greater than this number, these numbers right here, would you reject the null hypothesis and then conclude that the data is not consistent with the expected ratio.